So continuing on with 13.1 and getting into 13.2, here we have this graph for kinetic energy and temperature, and it's a distribution plot. And we have two different things plotted here. So we have a colder sample and a warmer sample. So with our colder sample, which is the blue line, we can see that we have a narrower curve. It is more narrow, okay? And we have a much, the mode here, okay, which is the central part, the top of the curve, there's a higher number of molecules at that mode, and the mode is the most common kinetic energy, or the most commonly occurring value. So I think that you probably go over mode and median and mean in your math class. So we're just going to be using that here because it's a more accurate way to describe these graphs and what we're actually calculating or looking at, rather than the word average, for example. So mode, most commonly occurring value, and we have these two plots here. So we have our colder sample, the narrow curve, and a warmer sample is our wider curve. Okay, and so we have two modes for each of those. So our median, right, whenever we have a median, is our data point that's in the middle, okay, of all of our data points. And that median is not affected by other values, okay? Our mean is the sum of all data points divided by the total number of data points. Okay? So it's good to just have these three things written down to sort of define them, not only for your math class, but also what we're looking at here. And this graph is looking at the number of particles versus energy. Okay. So when we have a colder sample, we will have more molecules, okay, with a certain energy level, which is what you see there on the blue line. And when we have a warmer sample, we're going to be having less molecules at different energy levels along the curve. Okay. So now let's look into nature of liquids. Okay. So liquid particles slide past each other. Liquids flow. Okay. And this has to do with the kinetic energy of the particles. Okay, so as we've looked at before, intermolecular forces play a big part here. Intermolecular forces are basically zero for gases, practically. Okay, but they're not gases, or for liquids and solids. Okay, so they are. So in liquids and solids, the kinetic energy is great enough to overcome these intermolecular forces between some particles, but not all of them. And so those intermolecular forces allow those liquid particles to sort of stick to each other, and so they can slide past. Okay. Okay, so if some intermolecular forces, they won't stay static in one place if they can overcome some, but they're still attracted to one another, which makes them close. And this is why gases, particles in a gas, those particles are really far apart because they've overcome those intermolecular forces and they can't stick closely together or stay close together. Okay, and also liquids have this definite volume, this fixed volume, which we're going to talk about before, but also that they're together, the particles are together and they're not so far apart like in gases because they have a great enough intermolecular forces. The intermolecular forces are high enough to keep them together. Okay. And again, liquids maintain a fixed volume because of intermolecular forces. Okay. Particles are attracted to each other. Okay, particles are kept close. Okay, and this allows a fixed volume, unlike gases, which don't have a fixed volume. Okay, so liquids are amazing rare things, okay? They walk a fine line between too little and too much in terms of their intermolecular attraction. Again, we want intermolecular attraction in liquids so that those particles can stick together, but they can slide past each other because they can overcome some of this intermolecular attraction. So some naturally occurring liquids, mercury is naturally liquid, bromine is naturally liquid, obviously water is a really important liquid. So condensed, okay? These intermolecular forces reduce the amount of space between the particles in a liquid, so they're more dense than gases, okay? So increasing the pressure has little effect on the volume because it's condensed, okay? So if you go back and you think about how liquids look, the particles in liquids, remember they're close together. They're still densely packed with one another, and that's because of the intermolecular forces. They're still very close together because they have that attraction. Write this down for you. So if we increase the pressure, the volume isn't going to change because it's condensed. We can't condense a liquid more. Okay, we can't change the volume. All right. So vaporization, okay. We've sort of know about vaporization a little bit just from our time out in the world, right? In order for something to vaporize, liquid particles must have enough kinetic energy to overcome the attractive forces. Okay. Because vaporization, what it is it's a phase change, right? Remember phase change, which hopefully from liquid to gas. Okay. And evaporation, okay, is the process of vaporization at the surface of a liquid. And this is important because it's different than boiling. So, which particles in a sample will be the ones to undergo evaporation? Particles with the most energy. Okay, and this leaves slower molecules behind. Or molecules with less energy. Okay. So evaporation cools, and this is one of the mechanisms, you'll learn more about this in biology, but this is one of the mechanisms that allows cooling to take place when particles or sweat on our skin evaporates, right? It lowers the overall average temp of the remaining molecules because the particles with the greatest kinetic energy evaporate. They go from liquid to gas. Okay. And also requires energy to get sorry, I wanted to do that. It requires energy to get those particles to have a phase change, undergo a phase change. So it's releasing energy, it's taking energy away. Okay. Evaporation happens at faster at higher temperatures because the average kinetic energy is higher. Okay, more particles have the energy needed to overcome the intermolecular forces and escape as gases. So vapor pressure is the pressure that a vapor exerts above a liquid at equilibrium. Okay. And equilibrium exists in a container in which the rate of evaporation equals the rate of condensation. Okay, so this is what we mean here by equilibrium. Okay, the rate of the particles that are evaporating, they're going up. Evaporation is the same as the rate of condensation when those are returning from gas to a liquid. Okay. So liquids that evaporate rapidly have high vapor pressures, and they're called volatile. So often we hear the word volatile and we think it to mean explosive, right? But what it actually means is that they have high vapor pressure. They easily evaporate, which if we think about alcohol and we think about gasoline, those types of liquids, they evaporate very, very quickly. They easily go from liquid to gas, and also they're very flammable. So you can see where that word volatile comes into play. So what determines how high or low vapor pressure will be for a particular liquid? Basically the magnitude, again, we're talking about these intermolecular forces. So the magnitude of the intermolecular forces, how strong they are. This is why I wanted you to go back and do that simulation for intermolecular forces, because they're really, really important. They come into play in so many different concepts that we were discussing and we still will be discussing, and also that we'll look at next year in biology. Vapor pressure is measured by a manometer. Similar to a barometer, it again measures vapor pressure. So here we have vapor pressure and temperature, and here we have water, the third line. And you can see here that at 101.3 kPa, which is 1 atmosphere, right? This is the atmospheric level. Okay. Water will boil at 100 degrees C, right? Because the vapor pressure is equal to the pressure within the water, and so basically it is boiling. We're going to talk about this in a second. The vapor pressure and the atmospheric pressure are the same. So water will boil at 100 degrees C. You can see that chloroform boils at 60 degrees C at sea level. Ethanol boils at, it looks like a little bit less than 80, and ethanoic acid is much higher than water. It has a much higher boiling point. Okay. So vapor pressure is directly proportional to temperature, because as temperature increases, more particles have more energy to overcome intermolecular forces. It's all about those intermolecular forces. Okay. So boiling is different from evaporation because it's the process of vaporization throughout a liquid. Okay, not just at the surface. Okay, all parts of a liquid. Okay, so evaporation just happens at the surface, but boiling is happening all through the liquid. And this occurs when the vapor pressure is equal to the atmospheric pressure. Okay, so if we use that previous slide to determine the boiling point in Los Altos, for example, which is 1 atmosphere, we said the water, right, boiling point of water, okay, was 100 degrees C. We go back and look, right, we can see water is 100 degrees C. If we look at Lake Tahoe at 0.84, right, so Tahoe would be 0.84, if this is 90, and this is 101, so I'm looking at that, let's say, right here, so I'm going to say maybe 96, 97 degrees C. And Mount Everest is 0.32. So, I don't know, maybe here. Maybe 70. 70 degrees C, about. Okay, so I'm just basically using, and this is 101, so I'm like using it about 100, but that's 1 atmosphere, so I'm just using it, 0.84 is about right here, because this is 80 kPa. Hopefully you can see that relationship between them.